Okay, hey everyone. So thanks for being here at our seminar for one of the events that we're doing for the quantum program this fall. I just wanted to quickly announce a couple of upcoming events. So with that said, I wanted to just let our speakers take over. They're going to be talking heavily about their careers, so I don't need to do introductions. But yeah, I'm looking forward to everyone to speak and
Good. So my career path and a little bit about some interesting math problems along the way. Let's open with a question. What do you call a person who has been a postdoc for 10 years? Anybody know? Staff scientist. 10 years postdoc. I think that one's from John Yard, one of my favorites. So I wasn't quite a postdoc for 10 years, but I came close. So I got my math PhD in 2008 from the University of Connecticut. I then did a postdoc at the University of Waterloo, another one at Caltech, and then a third one at the University of Copenhagen. And then I became a research scientist here at UMD and a guest researcher at NIST. So, as part of the story, I'll try to kind of explain why it went down this way. So what did I do in grad school? So I started as a math PhD student. I was teaching calculus and linear algebra, and my kind of first interest was in analysis. So UConn, there was this kind of analysis superstar, Richard Bass there. Then I kind of switched to thinking a little bit about logic and computability with Reed Solomon. In fact, my first kind of talk that I gave at some sort of gathering outside my university was about theorems that are not provable in piano arithmetic, but are sort of comprehensible. So Reed, this prof that I was working with on logic, he had a copy of Mike and I, quantum computation and information, this famous textbook in his office. And so I borrowed it. I started kind of looking through it, and I found it really interesting. And so Reed connected me with Alex Russell, who is a prof at computer science and math. And there's Alex being very important. He probably laughed with this the picture I picked. And he's really the person who kind of, at least I would say, made it possible for me to have a career as an actual scientist. And he's an amazing guy. If you ever get a chance to meet him or work with him, I strongly encourage you to do so. So what did I do with Alex? So the first project with Alex was on decoherence and quantum walks. And it was great for me because I got to learn a little bit about, I had had a little bit of quantum mechanics before, but no quantum information theory. So it was a nice project for me. And I remember, the first meeting that we had about this, Alex sat me down and sort of like very enthusiastically explained the problem and all these things. And at the end he said, so this will really just boil down to diagonalizing a 4x4 matrix. And I thought, okay, I have no idea why it's going to boil down to that, but I can diagonalize a 4x4 matrix. So let me give this a try. So a few months later, I figured out what this 4x4 matrix that he was talking about actually was, and that was my first somewhat serious research project. So then I started working on hidden subgroup problems, and there I got to apply some representation theories or things of actual mathematics. In the end, my thesis turned out to be about uncertainty principles for compact groups, mostly because I really wanted to do something in pure math. So let me say a little bit about this hidden subgroup problem. So, you've all probably encountered Shor's factoring algorithm in some form, and you probably also know that its kind of core quantum computational component is this period finding algorithm, right? This oracle algorithm for finding a period of some function. And the key technique that sort of makes this all work is this quantum Fourier transform, which you can think about as a unitary basis change operator from the group basis of this vector space of complex valued functions of the cyclic group. So it sends the basis to the basis of characters. And it does so efficiently in some way. It's some sort of quantum mechanical analog of the DFT, or maybe more accurately, the FFT. So then people realized that, we can have much more general QFTs. We can talk about changing bases on, CG for an arbitrary group, from the group basis to the basis of characters for abelian groups. And then if you pass non-abelian groups, things get more complicated, but we still have some idea of how to deal with these things. Now this Fourier basis, the second basis G hat, becomes the set of matrix entries of irreducible representations. And now, for specific cases of non-abelian G, you get some interesting special cases, like the symmetric group is somehow connected to graph isomorphism, the dihedral group is somehow connected to hard lattice problems. And so there's kind of interesting things to think about there. This has kind of fallen out of fashion since then, but this was kind of the initial motivation. And okay, so here's kind of a problem that's still open in this area, which is, can you construct a quantum Fourier transform for compact Lie groups, and ideally come up with some interesting quantum algorithmic application for it. So this is still an open problem.
What makes that problem harder?
Sorry?
What makes that problem hard?
Well, for one thing, what's the group basis now? The group basis is now some continuous thing, so you have to somehow discretize the group. And then, you have to construct a unitary operator for this thing. It's not exactly clear how to do that. You get a unitary operator from Schur-Weil, but from Peter Weil. But that one's for the whole L2. So if you're discrete, there's lots of non-trivial things. But there are FFT algorithms for compact Lie groups, so that could be a starting point. So in my first postdoc, I kind of switched gears a little bit. In grad school, I really enjoyed algebraic topology, and I was looking for kind of new things to study in terms of quantum algorithms. And I got really interested in this area of TQFTs. So what happens there? So just a very, very high level. The idea here is to take some topological object, in this case I'm not, maybe a link, represent it as an element of some finitely generated group. In this case, this is the braid group. And then pick some unitary representation of that group. And thereby kind of turn this, in this case, we're turning this link into just a unitary operator. And then we can look at properties of this operator, and we can try to make these, we can try to do this in some way that respects topology. And what we get out at the end are, well, we get out some link invariants. And in particular, by following this construction in the right way, we actually get some quantum algorithms for approximating these. So then there's a 3-manifold version of this. So you can start with a 3-manifold, represented as a Heegard splitting, like a gluing of two handle bodies along some function f. The surface of the handle bodies you can also think about as kind of a discrete object if you do it in the right way. These functions you can express as a sequence of basic moves. This gives you this so-called mapping class group. And then if you pick the right kind of local representation of this mapping class group, you get 3-manifold invariants. So this was a lot of fun to work on, a lot of interesting mathematics, and kind of mostly what I did during my first postdoc, which was good because it got me a second postdoc at Caltech, which, okay, second postdoc, but it's at Caltech, so not too bad. And I got this, so I talked to John Preskel, and he later told me, yeah, basically it was because of these TQFT papers and Stephen Jordan saying that they should get me. And the whole time during the first and the second postdoc, I was applying to math departments, and it really wasn't going anywhere. I think, well, okay, we can talk later maybe about why that is, or my suspicions as to. So I kept working on TQFT stuff. I kept working on some problems on Lie groups, but it was sort of getting to the point where I kind of felt like maybe I would not end up as a faculty member at the math department, that I should do something else. Then I had this kind of weird and in retrospect, really bad idea. And the idea was as follows. So in my TQFT stuff, I learned that you can represent quantum circuits by these kind of topological things like braids. And braids admit a normal form. So, put 2 and 2 together, maybe there's a normal form for quantum circuits. And normal forms for circuits actually turn out to be kind of an interesting thing in cryptography because they kind of erase implementation details. So there's this thing called indistinguishability obfuscation in cryptography that people care a lot about. And for certain circuit classes, you can get indistinguishability obfuscations by just computing a normal form. Okay? So, this was, in retrospect, not a particularly interesting paper, but it did get me reading a lot of cryptography, in particular this paper on impossibility of obfuscating programs. So this paper shows that there's no algorithm that generically obfuscates classical circuits. And yeah, so reading this paper and related things got me really hooked on crypto. Some years later, I actually extended this result to show that you also can't obfuscate programs using quantum mechanics, but that's a bit later in the story. Yeah, so then I got my third postdoc, again, because of the TQFT and some of the rep theory work. Basically, I was chatting with Matthias Christandl, telling him about this stuff, and he said, oh, that sounds really great. Why don't you come to Copenhagen and do a postdoc with me? And I did, except I spent the whole postdoc learning crypto. Thankfully, Matthias was totally good with that. And, the first 2 years, I really kind of was just had my head down and perfect, thank you. Had my head down and was kind of learning cryptography. I mean, I knew some things about it before, but, in order to actually publish some papers, I guess you have to know a little more. But then in the last year, I had kind of quite a bit of success. I had a paper in crypto and one in Asia Crypto and one in Eurocrypt. And those are kind of the big 3 crypto conferences. So that was pretty good. So let me tell you just a little bit about one of these papers. This is this paper on building cryptography from hidden shifts. And hidden shifts are very closely related to the hidden subgroup problem. Okay, so this was nice for me, both because I got to work with Alex again and because I got to use some of the things that I did in grad school. So, in classical cryptography, there's this well-known construction of turning a public permutation into a private one by just saying, well, sample a random key. These are permutations on n-bit strings. So permutations of sets of size 2 to the n. So Evan and Mansour say, if you have a public permutation, you can make it private by selecting a string k uniformly at random, and then your private permutation will be XORing this key, apply the public permutation, and then XORing the key. So this is secure classically, and then these guys, QuICS and Morley, observed that quantumly it's actually insecure, and the reason is basically a hidden subgroup algorithm over the group Z mod 2. The model is a little fishy, like it requires quantum queries to this privately keyed object. So in terms of real security, this isn't an actual threat, but at least in terms of kind of theory, it's interesting. So, as soon as I saw this paper, I was like, well, I know how to fix the problem. The whole issue is that you're using this very special group where the hidden subgroup problem is easy. And if you just pass to another one, then the problem becomes hard for the hidden shift. Okay. So when I said hidden subgroup, I mean, it is hidden subgroup also over Z mod 2 to the n, but the key thing is that it's the hidden shift over that. So we just said, well, look, all you need to do is replace this XOR with a group operation over some arbitrary group. And now you get a hidden shift over, let's say, a cyclic group or a symmetric group or a dihedral group or what have you. And we sort of formalized this as this sort of G hidden shift assumption. We proved a bunch of nice things about it, like random self-reducibility. And then hardness, we could sort of argue based on all this previous work that people did on hidden subgroups and why that work failed. And actually, there's a nice open problem here as well, which is, can I use this exact same construction to turn a public unitary into a private? Yeah, I think that's a nice problem and probably requires some interesting math. So what about my current position where I am now? So right around the time that I was sort of starting to publish in cryptography, NIST started this process of standardizing post-quantum crypto. And one of the things that they wanted, kind of one of the types of people they wanted on their team were sort of quantum algorithms people that knew cryptography. My interview was on January 23rd, 2017. The reason I remember the date is that I gave the talk in the morning, then Matt Scholl offered me a position right after the talk. And then at lunch, he said, sorry, actually, you can't. We can't come because of the hiring freeze that was announced that morning. So I got a job. What do I do now? Basically, I'm kind of split between NIST and UMD. At NIST, I'm mostly working on this post-quantum crypto standardization process, which means evaluating post-quantum public key schemes and writing standards. At UMD, it's mostly research. So, I chase grants at the usual suspect. Occasionally I teach, like undergrad crypto, grad quantum. I guess next semester I'll teach undergrad quantum, supervising grad students and continuing to do research. And of course, my favorites are when I can do something that makes use of representation theory or something like that. Okay. So that all stuff.
Hey, hi everyone, and then thanks for having me here. It's like one more session about math and quantum. So just like I want to start with some brief introduction of myself. So just I'm currently a postdoc in quantum information science at QuICS at UMD, but I consider myself as a pretty much math people, and actually my background is really from applied math. So I did my undergrad in applied math from 2012 and 2016, and then I got my PhD from UC Berkeley, also in math department. Then after that, I just got this postdoc position here in quantum information science. It's really because at the middle point of my graduate studies, so I completely switched from applied math to quantum. So it's basically if you just look at maybe the first 7 years of my undergrad and grad, actually I'm going to doing something about what I call the applied math for quantum, but here this quantum really means the quantum mechanics or quantum physics. It has nothing to do with quantum computing or quantum information. So basically what I did at the first several years of my graduate studies, basically I just apply some numerical algorithms to solve Schrodinger equation or density functional theory or some computational physics problem. But at the middle point of my graduate study, I just completely switched from applied math to quantum. So currently I'm kind of working on quantum algorithm for applied math. It was basically so the core task is basically designing some kind of quantum algorithms, but the problems that I'm mainly considering is still the problems from scientific computing. That is, I'm working on quantum algorithms. So, but the quantum algorithms for some problems, including solving high-dimensional linear systems of equations or some Hamiltonian simulation problems. So the Hamiltonian simulation is basically quantum algorithms for solving Schrodinger equation. And also beyond Schrodinger equation, also did a lot of works on solving differential equations using quantum computing. So the reason that I made this switch, there are actually two reasons why I really made the switch. So the first reason is that I found out the quantum algorithms might be the solution of the challenging scientific computing tasks. That in classical scientific computing, so we're kind of stuck at the computational capability of the current computers. That is when we have very high dimensional problem, then classical computers are not that efficient. So probably you've heard of some terminology called the curse of dimensionality. That is for some partial differential equation, if the dimension increases, then your computational cost for if you use the classical computers will grow exponentially. So that is very, very expensive and not affordable. But for quantum computers, actually we can kind of expect the general cost, which is only polylogarithmic in terms of the dimension parameter, which means that so if quantum computers can come true physically, and then it probably provide a ultimate solution of many high dimensional problems in scientific computing. So I just feel okay, yeah, that is very exciting. I just feel it might be the next generation computational model for applied math and for computational math. So this is the first reason that I made a switch. And the second reason is that I found out there are lots of math in quantum algorithms or in designing and analyzing quantum algorithm. And I just feel like so our mathematicians can really, do a lot of cool stuff in quantum algorithms as well. So I'll just like kind of explain these two stuff in my today in talk. So I'm just like start with like why it is kind of like a general reason why I just feel like, why quantum algorithms may achieve kind of an exponential speed up in terms of the dimensions. So it's kind of like a very rough introduction on the computational model of quantum algorithms. So probably you have already heard this in the previous sessions in this kind of series on introduction to quantum computing. But I just want to kind of like make everyone on the same page. That is like, so for quantum algorithms, so basically like we have some kind of qubit, and then like for the single qubit, so if it is different from a classical bit, right? From the classical bit, so it can be either 0 and 1. So it can only be one of these two sides. But from the quantum bit or from the qubit, actually like we also have like a 0, we have a 1, but it can kind of like a quantum qubit can represent the superposition of these two different status. So basically like if we think of this in a mathematical perspective, that is actually like for the qubit, it contains the information of a two-dimensional vector, because like it can be both 0, it can be simultaneously 0 and 1. So basically like the information of a qubit is actually the probability of being 0 or the probability of being 1. So in a linear algebra language, that is, we can write the 0 to be the vector 1, 0, and we can write 1 to be the vector 0, 1. Basically like a qubit can be really represented as the vector alpha beta, where alpha square is the probability of getting 0 and beta is the probability of getting 1. So what we have said is that for the single qubit, it is kind of like a two-dimensional vector. Then for the general n-qubit system, so the basis can be constructed by the tensor product of many single qubits, but like in general, so we can just really view an n-qubit space as a linear space in dimension 2 to the power n, which means that we can represent an exponentially large linear space or linear Hilbert space only using a polylog cost, which is this little n. So, and that's this kind of like framework architecture makes me feel like, okay, so it is a very rough thought, but I just feel it is very useful when we start to look at the quantum algorithms from a mathematical perspective at the very beginning. That is, so for the quantum states, it's just like a high dimensional vector. And then like if you want to do some operations on these quantum states, we are doing some kind of linear transformations among those quantum states. And the quantum states they have to be normalized. So which means that we are kind of like doing some linear transformation among normalized high dimensional vectors. So which are exactly the unitary matrices. So which means that, so very roughly speaking, so we can really view the quantum algorithm to be some linear algebra operations, some linear algebra algorithm. And that is why I believe so we have many like useful mathematical tools, and we will use it everywhere when we try to like design and analyze quantum algorithms. That is, we will always use linear algebra because we are just doing some linear transformation. And especially we need a very, we will always use the probability theory because like the physical interpolation of a quantum state is actually like probabilistic. So we need some kind of like probability theory to estimate the probability that we really get some information from the quantum state. And of course, we need some numerical linear algebra matrix computations, but we really need like a very different perspective. So here it's really because like in the classical numerical linear algebra, so for example, we want to solve a linear system, we can use some like matrix multiplication, matrix vector multiplication, or some kind of like other intuitive method. But on a quantum computer, actually, like we have to do something completely different. So for example, we can, for efficiency, we can only use the unitary operators or a little bit something beyond the unitary operators. And then like we have to like restrict ourselves right here. And then like we have to really rethink all the algorithms from a different perspective. So like I'm just going to give you like two examples that I found. Okay, yeah, math can be really useful in designing quantum algorithms, and also like so the first example is really solving linear systems of equations. It's like the problem that I want to solve is this high-dimensional linear system, AX equals B. So it is probably the most important task in scientific computing. You know, like many other tasks can be really like reduced to solving a high-dimensional linear system. And if we think of classical algorithms, so for the classical algorithms, actually we will use some kind of Gaussian elimination or some factorization or some like iterative methods, but have to say that they're not very efficient on quantum algorithm. On quantum computers, we have to think some different ways. So what is efficient on a quantum computer? Actually, like because quantum computer is based on quantum, so we can somehow imagine that solving some quantum dynamics or simulating some quantum dynamics might be efficient. And it is indeed efficient because it is kind of like an independent question called Hamiltonian simulation, that is solving Schrödinger equation on a quantum computer can be very efficient. So the idea of this project is really like, okay, we know solving Schrödinger equation is efficient. And then if we want to study the linear system problem, then the natural idea is to reduce the linear system problem to a Schrödinger equation problem. So to do this kind of reduction, so basically like we start with the linear system and then we first formulate the linear system as an equivalent eigenvalue problem. So that is like we find a Hermitian matrix or a Hamiltonian H1 such that the eigenvector corresponding to the zero eigenvalue of H1 actually encodes the solution of my linear system. So if you look at right there, so we have the explicit construction of that matrix H1. So we have to do some kind of dilation trick to enlarge the dimension, but this construction is quite straightforward, which means that so we can solve this eigenvalue problem and then like we solve the original linear system. But after that, we are still like far from the Schrödinger equation, and then like the idea of like use the Schrödinger equation is called the adiabatic quantum computing or AQC. It's basically like the adiabatic quantum computing is kind of like a quantum computational model which can solve the eigenvalue problem by solving the Schrödinger equation. So it's basically like, so it is kind of like we have a Schrödinger equation right there, which is a time-dependent Schrödinger equation, and we have a Hamiltonian H of S, which is a interpolation between H0 and H1, where H1 is my target final Hermitian matrix, and H1 is some other matrix that I can construct before my calculation. I just want to make the H1, H0 to be very simple. And then the adiabatic quantum is based on the phenomenon that, so if we solve the if we start with the eigenvector of H0 and solve the Schrödinger equation, then the final solution of my Schrödinger equation will approximate the eigenvector of H1, which means that, so actually like it's kind of like weaving together the Schrödinger equation and the eigenvalue problem, and then like, yeah, we succeed. So, but like to weave this kind of together, actually like we have some kind of error, which is called the adiabatic theorem, which saying that, so if we have some assumption on my evolution time and on my Hamiltonian, then what we can get is exactly that my final solution will approximate the eigenvector problem. So we made this reduction. We from a linear system to an eigenvalue problem to the Schrödinger equation. And then like why math is useful right here. So it's really because in the second step, to formulate the eigenvalue problem to be a Schrödinger equation problem, actually like it is not an exact formulation. So we have some kind of error, which means that the solution of the Schrödinger equation is only an approximation of the eigenvalue problem. And then like we need to bound this error to really like make sure that our algorithm is indeed working. And basically like what we need to do is that we really need to kind of like derive some better error bounds between the solution of the Schrödinger equation and the eigenvalue problem, and also like try to reduce that error as small as possible. And you can really see that it is a well-defined math problem, and we can use some kind of real analysis techniques to really like, analyze this kind of errors. So yeah, this is like the first project that I found really interesting because like I can really reduce the quantum computing task to a well-defined math problem or applied math problem, and then I can apply my analysis tools to really like solve this problem. And another project that I found very interesting recently is kind of like solving general differential equation. So I'm considering like a differential equation, du dt equals negative a times u, but of course we can really generalize that to be time dependent and also with some kind of inhomogeneous term. And since here I'm considering this general linear differential equation, so the evolution operator is not necessarily a unitary operator. But again, if I want to use quantum computer, I also want to do some reduction. That is, I want to like kind of like relate my general non-unitary evolution operator to some unitary evolution operator or Hamiltonian simulation problem. And the way that we did is really based on this, what we call the linear combination of Hamiltonian simulation formula, which is e to the negative at equals an integral of some unitary operator. So basically, like if you look at this equation, that is like in this equation, so we have so for all the evolution operators, they are really unitary because we kind of like write A to be something like L plus IH, where L and H are the real parts and imaginary parts of my matrix A. So they are both Hermitian matrices, which means that in my integral, so the e to the power negative I times blah blah blah. So it is a exponential of a anti-Hermitian matrix, means that that is a unitary. So basically, like this equation tells you that, so we can represent the non-unitary evolution operator of a differential equation as a weighted continuous summation of many unitary operators, which means that we kind of like reduce the problem to the Hamiltonian simulation problem, and then like we can use our quantum computer to solve this differential equation based on this linear combination of Hamiltonian simulation formula. And of course, like to prove this formula is not that trivial. So here probably I don't have enough time, but like to prove this formula, so in some special case, it can be easy. So for example, like if you only have the L part, then it is trivial. And if you only have the H part, it is trivial. So if you only have the L part, it can directly derive from the Fourier transform. But the difficulty is really to combine these two parts together. And the technique that we use is some technique in complex analysis. That is, we use some kind of Cauchy's integral theorem to prove the interaction term is vanishing. And then we kind of like combine these two special cases together and prove like a general form, which can be really useful in designing quantum algorithm. And here is like another real cool project that I found. Okay, yeah, the complex analysis can also be very useful in quantum algorithms, which I which I did not expect before I really like go through this kind of project. Okay, so that's pretty much that I have. So basically, like I made my switch from applied math to quantum at the middle point of my graduate study, and actually there are like two reasons. So first, I feel like it is the solution of high-dimensional scientific computing problem, and the second, I just feel like actually like math or applied math, because my background is really only from applied math, so it can be very useful in designing quantum algorithms. That is, we will use some linear algebra, we use some probability theory, we use some kind of even some real and complex analysis tools. And with that, I'd like to conclude. Thanks.
Great. So it's great to be part of this event. My impression in general is the intersection between math and quantum in the past has been somewhat uncharted territory. And this gives us an opportunity to maybe map it out a little bit more and make it more structured. So I'm Carl Miller. I work in the Atlantic building that's next door. I will also just dive in with this very short version of my professional history and how I got here. So originally I was a math PhD at Berkeley. I worked on algebraic geometry, fairly pure subjects, not entirely pure, but mostly. And I worked on the arithmetic side of that. And then I was a math postdoc at Michigan, because that happened to be a good place for algebraic geometry. And it was there that I started to get some more applied interests. I looked at a lot of different things, and the thing that I was most interested in was quantum information. The very first quantum event I ever went to was the Michigan Quantum Summer School in 2008. I have vivid memories of that. I didn't really understand a whole lot, but I remember in particular talk by Chris Monroe, where we had some vivid pictures of ion traps. It seemed like a really interesting subject. So during that time, I chased down a lot of possibilities and tried a lot of things, many of which didn't work. But one of the things that did work was that I connected with Yayan Shi in the computer science department in Michigan, and we arranged for me to be a research fellow, which is sort of just another name for a postdoc in CS at Michigan, and do quantum information there. So officially I was a postdoc for 9 years. I think we're tied there. Okay, 9 years. Yeah. And for me, one of the reasons it was 9 years was because the intermediate years, 2010 through around 2012, was sort of like going to grad school again and learning a new subject. And I would say a lot of the same kind of thinking I ended up using in that I had done in grad school, I did here, but there was also a lot of new stuff that needed to be learned, foundational stuff. So going into the postdoc, I didn't really have much background in CS. It was so I got interested in quantum, and that motivated me to start learning the CS side. And then the sort of transitional years, one of the first things I did was I taught a class on coding theory, and which is a highly mathematical subject, but of course it's also based in computer science. And that was one of the few things I did that was sort of in between the two. And there was a time when I was going back and forth between the two departments, which is actually not so convenient because they're in different campuses, but not happening all apart. But yeah, that was so it was kind of a gradual transition over about a year or two. Cool, and then I had a research breakthrough in 2013, which I'll talk about later, which was on device independent quantum information. And then a few years later, I landed here, and I'm currently both at NIST and also at the Atlantic building at QuICS. Okay, so this is mainly going to be an optimistic talk, but there were two cautionary notes that I've thrown in, some of which may have already been covered, but I figured they were worth saying. So one is when moving between fields depends a lot on when you're doing it, and it can be very different depending on when. I would say moving into a new field as a grad student is a great thing to do. That's what grad school is for. It's a good time to explore, and people expect that. Moving into a new field as a postdoc looks more like that. And this is not to say it is impossible, but it can be very difficult. And I have a few data points on this, including myself. It is the same support structures are not entirely there. So I say this because I think there are a lot of students in the room, and I think, so I say this because grad school is a great time to decide what you really want to commit to. It gets harder later on. So that's one cautionary note, and another cautionary note, which I've included once before in the talk, is just to know the difference between appearance and reality when it comes to the research process. If you look at somebody's CV, you see just the success. The reality is there's in between lots of learning, and usually, projects that didn't work out, but the successes are ultimately the ones that count. Okay, so with that said, since time is limited, I'm going to be focusing on the successes and not so much on the intermediate work. So I'm going to talk about 3 different projects, and my goal here is to try to identify things that worked well. Since partly because we do want to kind of map out the territory between math and quantum, figure out what in the research process can help us to get to where we want to go. So starting with device independent random number generation, this is the first major topic that I was able to get something on. And as we're going to see, math came into it kind of later in the stage. First, I had to learn a lot about the CS part, but then it did eventually turn into a math problem. So the problem is, can a user generate random numbers from a Bell experiment? The Bell experiment is originally something from physics. It was designed to test the existence of entanglement. And the basic idea is you have 2 stations which are separated in space, and we don't make any assumptions about what these black boxes are doing, but we do assume that they can't communicate. And then based on that, if there's a certain, we play a game with them, and if the average score is above a certain level, we conclude there must be entanglement there. Somebody had the insight much later that we can not only verify entanglement, we can also verify randomness, which is very useful for cryptography. That was proposed in 2007, but the theory was not there to prove it. And so we started working on this around 2011. There had been a few papers on it, but the big challenge was we were working with randomness in the presence of quantum side information. And the tools to analyze that just didn't exist at the time. We had all these tools for the classical case, which could be used to prove limited security proofs, but there was not the right tools, the right concepts to deal with quantum side information. So what we ultimately were able to prove, we provided the first error tolerant security proof against quantum side information for random numbers coming from a Bell experiment. And the big deal about quantum side information is you want this, when you're dealing with cryptographic protocols involving quantum devices, you need to deal with the possibility that if you have 2 processes going on at the same time, they could be entangled, and we still want them to be secure in that case. And so we invented some tools. We took tools from existing literature and we put that together and produced 2 papers. The first one was quite long, and then the second one we simplified the proof and strengthened it a little bit and made it more accessible. What went well in this case? So first I would say choosing the right problem at the right time. The reason this was a particularly good problem when we found it, when my co-author Yang and Shi found it, was because there were parallel developments and experiment that were going on right at the same time, like just the year before, there had been an experiment done on this. And there was a small community of expert researchers working on it. Which for me, with my style, is kind of ideal. It's nice to have a problem where there's just, you know, several others, but not too many other researchers who are working on it. Then we know our research will be appreciated, but we're also not going to be drowned out by a huge field of competition. So that part worked out well. And then also, ultimately, the way that we solved it was by relating it to a simple math problem. And often, if there's a problem that has, you know, that the researchers are finding difficult, is because there's something underneath it that is mathematically hard. And in our case, it came down to simple questions about the geometry of the Schotten norm for matrices, uniform convexity and uniform concavity of the Schotten matrix norm. And so after going through lots and lots of derivations, lots and lots of reductions, we reduced it to that, and then found in the literature some theorems about that geometry with which we solved it. Okay, so that was research topic number 1. Number 2 was something more recent, quantum coin flipping. Also involves generating a random number, but in a different scenario. Here we have 2 parties, and they are interacting, and they just want to generate 1 bit. But the key is they have competing interests, and they want to be able to do it in a way where they're both assured that the bit is fairly generated. And they want to do this using quantum communication. And ultimately, this is, you can boil this down to just a math question. What we're asking for is whether we can specify quantum states and quantum operations that these parties can prepare and exchange in such a way that the ultimate outcome when they measure at the end will be a fair coin flip. Challenge is, if we do phrase it that way, that we have this giant search space and it's very hard to find. And at the time that I was looking at this, the best known protocols for quantum coin flipping were both very complex and very inefficient. They've been proved to exist, but they could hardly even be written down, and they were very inefficient in terms of the number of communication routes between the 2 parties. And this was despite the fact that the problem had gotten a lot of study. So we, the theory was there to do this, but we could not do anything practically. So what I was able to prove was that actually there's reason for all that. Any quantum coin flipping protocol must use exponentially many rounds of communication. That's exponential and reciprocal of the bias. And so what that essentially showed was that we're not going to be able to do that much better than the existing protocols that are already out there. And there's a reason this can't be done efficiently. And that was done in that paper. What went well in this case? So this is a negative result. The previous one was a positive result. The community appreciates both. In this case, one key thing was doing a deep study of previous work by others. I was able, in this case, to just write a fairly short paper on this, unlike the device-independent random number generation protocol. And that was probably because we were building on previous work by people like Carlos Machon and Alexei Kitaya. And knowing that was vital to being able to get the result. Computer experimentation, I hadn't used that so much in other projects, but I did use it a lot in this one. Originally, I was seeking to find efficient quantum coin flipping protocols, and I tried just searching for them using Mathematica, and the search kept not working. And tried it from many different angles, and it kept not working. And eventually, that led me to think, okay, well, actually, there's some kind of obstruction here. Can we actually map out the shape of the obstruction? And that's where the result came from. And then, likewise, as with the previous project, relating the question to a simple math problem. And I talked about this in the quantum math writ, and I won't be going into much detail here, but basically there was this very simple problem about the shape of rational functions with real poles. I wanted to find rational functions that had this particular pinched shape and couldn't seem to do it. And then was able to get help from a math professor in figuring out that actually there's a reason these are very hard to construct because the poles are exponentially large. And that was sort of the underlying key to the impossibility proof, and then we just trace back from that and get the complexity result. Okay, and last and most recent, this was a more abstract question, also dealing with the Bell scenario, the complexity of Bell experiments. So if we take the Bell experiment that we're looking at random number generation and look at it in a more general sense, and just say like, okay, well, we're doing a Bell experiment, 2 stations. We have some input from a finite set, some outputs from a finite set, And the question is, what kind of conditional probability distributions can we get in this case? And this comes up over and over again in cryptography, anything involving two stations in cryptography, this is bound to be relevant. And what we're really asking for here is, what is the nature of a quantum correlation between the two QuICS? How do we know if something's quantum or when it's not? And the reason this is hard is because we are essentially searching over a space of unbounded dimension. So there is no upper limit on how much entanglement you might need to achieve a quantum correlation. So the only way to, the naive way to answer this problem would be to just keep searching over all possible entangled states. But that set is of unbounded dimension, so you can't do that in a guaranteed way. What we were able to show was that this problem is computationally impossible in a very strong sense. So even if we were to restrict the inputs and the outputs to a fixed finite alphabet of a certain size, then the quantum membership problem would be undecidable. And there is actually no algorithm that will tell you for certain whether a given correlation is quantum or it's not. Previously, this was known for arbitrarily large unbounded alphabets, and we were able to prove it for an alphabet of finite size. And that was the paper, and that was Hong Hao Ku's thesis when he was here as a student. Well, in this case, so one big thing was having team members with special knowledge and expertise. As I was saying before, it was nice to have a deep study of previous work. In this case, it's even better when you have a team member who has done some of the most important previous work, and that was William Slofter. And also, Hong Hao Ku, a very good technical writer who has formal background both in math and quantum. So there's that, and then also in this case, I would say choosing the right problem at the right time. This, I think, is particularly important when we're dealing with a theoretical problem rather than an application-oriented problem. So since this is mainly an abstract problem, I think it was important that we knew that there was already a community that was interested in this. Computational complexity of quantum processes was a very big question at that time, and particularly multi-party interaction. Lots was being done on it, and so we knew that there was a community that would appreciate the result. And that is the end of my talk. Thank you.
I'm going to display this on the screen. We appreciate your feedback, so you can take a picture of that QR code or the link.